All right, in this video we're going to look at maybe one of my favorite antiderivatives, exponential functions. So before we do that, let's recall the derivatives of the exponential functions. Let's recall the derivatives. So first of all, let's recall the most simple exponential derivative, that of e to the x. So the derivative of e to the x is, in fact, my favorite derivative because it is its own derivative. Okay? And so this, of course, makes the antiderivative very simple as well. So let's see what this tells us about the antiderivative. So if I want the antiderivative of e to the x with respect to x, that's asking, what do I need to differentiate to get e to the x? And the answer is, well, I need to differentiate e to the x to get e to the x. Now, that's not the whole story, because whenever we're doing antiderivative, we're looking for the most general antiderivative that exists. And as we already know, there are many antiderivatives, an infinite number for any function. And so we need to tack on the arbitrary constant c, because now if I differentiate this function over here, no matter what c is, I will always get e to the x. So that is my favorite derivative and antiderivative. But what do we do in the case where it's not e to the x, it's some other number to the x power? So let's recall that derivative. It's one that's easily forgotten, a to the x. Well, it starts the same way as e to the x. It repeats itself as its own derivative. And I'm going to leave a space here because it's not the whole story. It is, in fact, the whole story if the base a happens to be e. But if you recall, when you differentiate a base that's not e, you get a to the x, but you also get the coefficient of the natural log of a. So when we differentiate 2 to the x, for example, we get the natural log of 2 as the coefficient times the function 2 to the x. So the function still repeats itself, we just get this extra adjusted coefficient. Okay? So what does this tell us about the antiderivative? The antiderivative of a to the x. It's not quite as straightforward as e to the x, but we can go through the same process. We can ask ourselves, what do we differentiate to get a to the x? And we're going to start with a to the x. That's a good starting point, because if I differentiate a to the x, I'm definitely going to get a to the x, but I'm going to get some extra stuff. If I differentiate a to the x, I'm going to get the a to the x, but I'm also going to get multiplication by the coefficient natural log of a. So what I need to do in my antiderivative is build in a coefficient that will counteract the natural log of a coefficient. And it's very simple to do. I just build in the reciprocal of the natural log of a as my coefficient. So the antiderivative of a to the x is a to the x with a reciprocal coefficient 1 over the natural log of a. And of course, we don't want to forget adding on our plus c. Now you can check this out. Let's do that. So first of all, that is the antiderivative. Let's see why that's the case. If you're having trouble visualizing what I'm describing, if I check it, you can check it through differentiation. So that means if I differentiate the right side, 1 over the natural log of a times a to the x plus a constant c, well, I'll keep my 1 over natural log of a, it's just a coefficient. But then I'll have to differentiate a to the x, which gives me natural log of a times a to the x. And then plus c, when I differentiate, turns to 0. And you can see now what happens when you multiply the derivative coefficient by the antiderivative coefficient, they turn into 1, thus giving us, in fact, that the derivative of this guy is a to the x, which is what we want. So be a little more careful when your base is not e. Another thing to notice is that these ideas work even when your base is e. Because if your base is e, this turns into the natural log of e, which is 1. And here, if your base is e, this turns into 1 over the natural log of e, which is also 1. So this formula works even in the case of e. In fact, these concepts, when you're dealing with exponential functions, we're limiting ourselves to a values that are bigger than 0. Let's see. A is between 0 and 1, or a is bigger than 1. So we don't want any negative a values, and we don't want an a value that equals 1, because 1 to the x is just a constant function. It's not actually, doesn't fit the concepts of exponential functions. It's much simpler than that. So these are your exponential antiderivatives. Good luck.